In this video, we're going to talk about exponential growth and exponential decay in real-world contexts. Okay, so we're going to be able to write an equation for an exponential function in a real-world context. So when we're looking at exponential functions, they come in two forms. They either come in growth or decay. The equation is the same for either growth or decay. You're still going to use y equals a times b to the x power. And what you'll remember from our last video was that a is going to tell us our starting value and b is going to tell us our multiplier. Okay, so that's just a little bit of a review from last time. We're going to talk a little bit about what the value of b looks like. So if something is growing over time, then the value of b is greater than 1. So our multiplier, if we multiply by something greater than 1, then it's going to make that number bigger. So that's why when we think about b as our multiplier, if it's greater than 1, we're going to see growth. If the value of b is less than 1, if we're multiplying by something less than 1, such as 1/2 or 2/3 or 0.1 or 0.6, then we know that the value of the number we're multiplying by is going to get smaller each time, so that's why it's going to be decay. And sometimes we're going to talk about growing or decaying at a fixed percent. So it says, oh, the population is growing by 20%, or the bacteria are decaying at a rate of 60% or something like that. And if we're using a percent for exponential growth, you're going to use 1 plus r as our value of b. So that means I'm going to take 1 plus the percent. So if it was growing at 20%, for example, I would use 1.2. If it was growing at 5%, I would use 1.05 for my b, for my multiplier. And if it's decaying at a fixed percent, I'm going to use 1 minus r. So for example, if it was decaying by 20%, I would use 0.8 because it's going to be 80% of its original size. That's what I'm going to multiply by, 1 minus 0.2. Okay, that's what I use in my multiplier. Or if it's decaying by 5%, I would use 0.95. That's 1 minus 0.05. Okay, because if it's decaying by 5%, then I'm going to have a population that's 95% of its original each time. And then I've just got an example in your notes of what these might look like. Exponential functions are a curve, because basically our function is steadily increasing. Our rate of change is not constant. It is getting greater and greater every time. So our slope between our first 2 points is very gradual, and then as I keep going on exponential growth, let's look at these 2 points. Between 9 and 10, the slope's a little bit more. Then between 10 and 11, the slope's even bigger. Then between 11 and 12, it's bigger, and then it keeps getting greater and greater and greater. And when you do decay, it's the opposite. It's going to get small quickly, and then the rate of change is going to get smaller and smaller as we go. Okay? So let's look at two examples. So first of all, bacteria multiplying at an alarming rate. When I see this word that bacteria is multiplying, that makes me feel like we're probably dealing with exponential growth. Okay? Each bacteria splits into 2 new cells, thus doubling. Okay? So we start with only 1 bacteria. It's going to double every hour. How many bacteria will they be only after 12 hours? So we're going to write an exponential equation. First, I'm just going to draw the situation. So we start with 1 bacteria. It splits into 2 more. Each of those split into 2 more. Then each of those split into 2 more. So on and so forth. And I want to know, this is each hour. So this is at the 0 hour. This is at the beginning. This is after 1 hour. This is after 2 hours. This is after 3 hours. So on and so forth. So thinking about it in a table, which is what we are comfortable with for equations, I can look at x as hours and bacteria There's 1, then there's 2, then 4, then 8. So I'm looking at an equation that is y equals 1 times 2 to the x. I start with 1, I'm doubling every time. And then use it to find the answer. I want to know after 12 hours. So I'm going to do 1 times 2 to the 12th. I'm going to find the answer to 2 to the 12th power. $4,096. And then if there was a different amount of bacteria other than 1 at my start, then I would multiply that by that number. But since that's not the case, there would be 4,096 bacteria cells at the end of 12 hours. Okay, and then we're talking about a new car in this next one. It says that when you drive a new car off the lot, it decreases in its value by about 20% each year. So we're decreasing in value. We're looking at exponential decay, and it's 20% every year. So the car is $16,000, and we want to find the value over time. So when we're using 20%, that rate that it's losing is by 0.2. And so to find the multiplier, I'm going to multiply by, I'm going to do 1 minus the rate, which means I'm basically going to do 1 instead of minus rate, minus my value for rate, which is 20%. So that means I'm going to be multiplying by 0.8, because basically my car started off at $16,000, and then when I multiply that by 0.8, that's going to tell me the value of my car at 80% of its original value, which is taking 20% off. So that's 12,800. Okay? And so on and so forth every year. So writing my equation, I'm going to use y equals 16,000. That's my starting value. And I'm going to multiply by 0.8 to the x power. I'm going to multiply by 0.8 for times however many years I'm looking for. I'm looking for 5 years, so I'm going to do 16,000 times 0.8 to the 5th power. So the first thing I'm going to do is the exponent. I'm going to take 0.8 to the 5th power, 0.32768. And I'm going to multiply that by 16,000. $5,242.88. So I find that after only 5 years, already my car that was worth $16,000 is now only worth $5,242.88. All right, so what I want you to do is to look at this before class question and go ahead and write an equation for this situation and answer the question how much money he has after 12 years.